Hello everyone. I'm Daniel Letros here from the University of Saskatchewan. Today talked about the aerosol limb imager, or ALI. It's a multispectral polarimetric imager that we use for the observation of atmospheric aerosol and cloud. Now earlier in this conference you heard a presentation given on Tuesday about the HAWK mission. ALI is a part of that mission, but I'm not here to talk about that right now. Rather, I'm just here to discuss some demonstration that the University of Saskatchewan has done with ALI on stratospheric ballooning. So to that end, the most recent iteration of ALI that the University of Saskatchewan has for stratospheric ballooning has flown twice, once in the S-Range facility in 2021, and more recently in Timmins, Canada of 2022. Now ALI is a limb imager, as the name suggests. So we actually take a picture of the limb, and we take this picture at anywhere from between 500 and 1500 nanometers, so it's actually a filtered image. And we use this information to retrieve aerosol extinction, as well as to try to get us some particle size information. Additionally, each of these images are polarimetrically filtered as well. So they're made of only either horizontally or vertically polarized light of the atmosphere. Now there's been a lot of satellite talk in this conference, so just to kind of remind everyone about the kind of geometry we face with stratospheric ballooning. Typically these balloons float at an altitude of about 35 kilometers. Now we design our version of ALI to have a 6-degree vertical field of view. So from this height, basically we measure from the float altitude of the gondola all the way down to the ground. In this cone, we get 640 spatial samples, which yields about 100 or less meters of tangent altitude resolution. Additionally, ALI also wishes to find the top of the cloud deck. And while the polarimetric information is useful for the aerosol retrieval, it's also very useful to do this. So the idea here is we want to find where the top of the cloud deck is, so we know where it actually cut off for retrieval and just sort of retrieve in a cloud-free region. So to kind of go into how ALI works, this is actually a picture of the optics box that we fly on these balloons. So everything kind of in the top left over here. This is just a telescopic system that we use. So baffle, an aperture stop, a mirror, a field stop, and another mirror. And this system just maps our 6-degree external atmospheric field of view into our limiting aperture, which is the spectral and polarization selection subsystem, which we call the SPS. Now this SPS is actually the heart of ALI, and I'm going to talk more about it on the next slide. But this does the polarimetric and the wavelength filtering. This operates in collimated space, so the collimated output of this then gets focused by this third mirror onto this detector, capable of measuring both the visible and shortwave infrared radiation. So the SPS, it works by a series of 4 components. The first one being a liquid crystal rotator. What this component lets us do is essentially select whether or not we want to rotate the incoming polarization states of the atmosphere by 90 degrees. So in this kind of simplified diagram here at the bottom, say the horizontally polarized light of the atmosphere is in the red bars, vertical in the blue. As it passes through the first component, we can optionally rotate it such that the horizontal light of the atmosphere is now vertical or vertically polarized within our instrument. Or we cannot and just simply pass all the states so that the vertical light of the atmosphere is still vertical within our instrument. This then passes through the second component, which is a vertical polarizer. It just selects the state we wish to measure. And then this gets fed into acousto-optical tunable filter, or AOTF. Now I imagine some people here are familiar with an AOTF, but just in case you're not, it is kind of what the name suggests. It's just a tunable optical filter. These devices are made of like a birefringent crystal with a transducer on the side. You can tune the transducer to vibrate the crystal at different frequencies. Depending on the frequency you vibrate it at, a wavelength of light will respond to it and diffract off onto a different optical path. So what this kind of looks like just functionally is you have these filter shapes provided by the AOTF, and depending how you've tuned this transducer, you can slide this filter shape around in wavelength. This filter shape kind of defines the spectral resolution of our instrument. So the full of half max of this shape defines our resolution at any particular wavelength, and it is wavelength dependent. So we get resolutions anywhere from 1.5 to 13 nanometers in wavelength. Interestingly enough, this diffraction process, which filters the light, will also rotate the polarization again. So as we have the vertical light going into the AOTF, this diffracted light, whatever we decide we want to image, gets rotated to be horizontal. So the broadband unwanted light then hits our fourth component, which is a horizontal polarizer, to eliminate it, and then we pass through our monochromatic light of whatever polarization state of the atmosphere we wish to measure. So what does this actually look like in practice? Well, here are some images from our Sweden campaign in 2021. Before I continue, just note these black dots here, these are just non-ideal pixels we decided to discard in the scientific processing. But either way, both of these images are actually of the same atmospheric scene, and they're both taken at 1025 nanometers. Except the left one here is of just the horizontal polarization, and the right one is of the vertical polarization. And you can see just even visually the polarimetric effects of the atmosphere and how it actually is perceived by LE. And there's actually some quite useful information in this polarimetry. So LE nominally measures at these 10 wavelengths up here, ranging from 710 to 1450 nanometers. This range of wavelengths we decided to measure is basically just to avoid contamination from other atmospheric constituents. But LE goes and it measures each of these wavelengths, and it measures one polarization state right after the other. And we go through and we aggregate all these images, and we produce these radiance profiles. And these radiance profiles are what we fit into, or what we feed into the retrieval. So we go about aggregating these radiance profiles as one might expect. We take these images we collect, and then we do some manner of a cross-track binning. So this could be just as simply as we take a single column, and that's a radiance profile, or we select the whole image, a subsection of the image, bin it together to produce these radiance profiles. Now, because it's a polarimetric imager, each of these radiance profiles are polarimetrically resolved, so we can use them to reconstruct the Stokes parameters of I and Q, I being the sort of total representation of light, and Q being either the vertically or the horizontally proportion of light, which I've done right here in these two plots. Furthermore, because now we have these, we can then take Q and divide it by I to make a degree of linear polarization, essentially, all altitudinally resolved. And then we can use this information, and this is basically how we go about finding the cloud deck. So on this next slide here, along the y-axis, I have the ratio, or the degree of polarization at 1025 nanometers, and I divided by that at 750 nanometers. And along the x, I just have the Q of I at 750 nanometers. Each of these dots is taken from a particular altitude of the Q over I ratio profile. And you can see that in this kind of Stokes parameterization space here, we get this nice nice segregation of these two clumps here, with all these high altitudes making up this clump, and the low altitudes making up this clump. Now, just as a demonstration, if I take this kind of one transitional point here, look up its tangent altitude, and plot it against the original radiance profiles I aggregated, you can see it shows up right above the cloud deck, or like right where you start seeing cloud features actually show up in the radiance profiles. The nice thing about this is this is a very quantitative way at working out where the cloud deck is, rather than just deciding to cut it off at some point you might think is nice. Yep. And then we take these radiance profiles and we feed them to the retrieval. So an example retrieval I'm going to show here. This just follows the usual kind of retrieval methodology that Rogers has described in his book. For our forward modeling, we use Sastran, which produces me-scatter radiance profiles as well as polarized weighting functions, and this kind of ability that makes this retrieval pretty possible. So what I've done here is I've taken two wavelengths. I've taken 750 nanometers as well as our 1450 nanometer wavelength, and I've taken both polarization states of them. The next thing I do is I bin by tangent altitude down to the resolution of my retrieval grid. In this example is 300 meters. And then this is a bit of an unfortunate step I do, but I take the two wavelengths and I average their polarimetric profiles together. This is simply just to reduce the complexity of the measurement vectors the retrieval is trying to retrieve on. I am throwing some information here, throwing away some information here. I would rather not. But for now, I'm having some trouble fitting to more complicated measurement vectors, but this is still a really nice way of making measurement vectors which are still polarimetrically dependent. But then I take these average profiles and I do what's usual for radiance or aerosol retrievals, is I high altitude normalize them, take the logarithm of the profiles, and I also truncate them to the cloud deck. In this case, this cloud deck was found about 13 kilometers, and I use the same Stokes parameterization I described before. Additionally, as these profiles are getting made, all the same steps are done to Rayleigh profiles. So that is, these are radiances still polarimetrically resolved, produced by SAS-Tran in simulation for an atmosphere that has no aerosol in it. As a final step to produce the measurement vectors, I take these solid profiles here, and I subtract off the dashed ones. These are the Rayleigh profiles. And you get these profiles here, which now are essentially just a contribution above our simulated no aerosol atmosphere. And this is what we retrieve on. So in the retrieval itself, I treat the aerosol size distribution as log normal. I fix the width of this log normal size distribution to be 1.6. And my state vector actually consists of both the number density and the particle size median radius. And you can see the results of this example retrieval right here. So on the top, these dots are the same measurement vectors I just constructed. The solid lines are that of the retrieval as it's finished converging. And then, I retrieve this number density, this particle size median radius, and you can see this kind of layer of larger particles just below 25 kilometers. Now, I should also mention, just to be clear, that this data was taken from our Timmins flight. So it's actually real data, it's a real retrieval. So sort of validate this, what I did is I took all this retrieval and I wrapped it up back into extinction at 750 nanometers. And then I collected measurements from all of OSIRIS, OMS, and SAGE. So I just show kind of the coincidence here on the left with OSIRIS in green, OMS in orange, SAGE in blue, and our LE measurement from the balloon in red down here. And all the extinctions from all these instruments, LE being in red. And you can see that actually our fitted extinction looks quite nice compared to the other instruments. I think there's pretty good agreement. Unfortunately, at least for now, we do have larger error bars. This error is driven by the larger error due to the particle size retrieval. But work to fix that is ongoing. First step being to learn how to fit to more complicated measurement vectors and kind of avoid that step of averaging the profiles together. But yeah, overall I think it's rather encouraging. And that's kind of what Ali can do at the moment. And yeah, thank you for your time.